Imagine this, a ship weighing thousands of tons, out in the middle of the ocean, holding its position so perfectly it looks like it's frozen in place. It's an incredible piece of technology, until it isn't, until that stable platform becomes an uncontrollable force of nature.
All right, welcome to the bridge. Consider this your briefing. We're going to cover the critical systems that keep this vessel where it's supposed to be. We'll start with how we create that illusion of stability, then dig into the three main things that can go wrong: the power, the perception, and the brain. And then we'll talk about the most important system on board: you.
So first up, holding steady at sea, or as you should really think of it, the illusion of stability. The magic trick here is what's called a dynamic positioning system, or DP for short. Just think of it like a super smart computer brand that's in a constant battle with the wind, the waves, and the current. It's using the ship's own thrusters, making thousands of tiny adjustments every minute, just to keep us perfectly still.
It's a seriously impressive system, but the most important question you can ever ask up here is always going to be the same. What happens when it breaks?
Well, a failure usually comes in one of two flavors. The first is called a drift-off. This is what we'd call a passive failure. Basically, we lose our ability to push back, and the ocean just pushes us around. It's bad, for sure, but it's predictable. The second kind, and this one is way more dangerous, is a drive-off. This is an active failure. The system gets some bad info, a thruster goes haywire, and the ship uses its own power to literally drive itself uncontrollably away from where it's supposed to be.
Okay, let's look at our first major point of failure. Section 2, propulsion. This is what we call the power problem.
And this isn't some rare, abstract risk. Just look at these numbers. Between 2007 and 2015, there were 116 incidents tied directly to the propulsion system. And in 24 of those, the ship completely lost its position. This stuff happens.
This diagram shows you how a drift-off can be like a domino effect. It's almost never just one big thing breaking. It can start with something tiny, a weird feedback signal, a leak in a hydraulic line, a problem in a control panel. But any one of those little things can cascade into total propulsion failure, leaving the ship dead in the water and at the mercy of the sea.
So what does that look like in practice? Well, a thruster might just stop responding to commands, or it might fail to return to a neutral zero-thrust position. Sometimes the ship's own safety systems will shut it down because of something like a cooling system failure. And sometimes the cause is just bizarre. Get this. In one real incident, a thruster was physically pointing 180 degrees opposite of what the indicator on the bridge was telling the crew. The computer thought it was pushing to port, but the thruster was actually pushing to starboard. The result? The ship's thrusters started fighting each other to a complete standstill, and the vessel just drifted away.
Now let's talk about the more violent failure, the drive-off. This happens when a thruster doesn't just fail, it goes rogue. A signal error or some mechanical problem causes it to jam at full or near full power. The DP computer tries to fight it, of course, using the other thrusters, but you can't win against a rogue engine. The vessel is just powerfully shoved off its mark.
So that's the ship's muscle. Now let's talk about its eyes and ears. Section 3, sensors. This is the perception problem.
And this is a huge deal. In that same time period, we saw 99 incidents caused by failures in the position reference systems. The actual sensors that tell the computer where in the world the ship is.
And what's really fascinating here is when you break down what causes these sensor-related drive-offs, the data is crystal clear. The most common sensor we use, the satellite-based DGNSS system, is the #1 culprit by a long shot.
And this schematic shows us exactly why. It all comes down to bad data. You get some interference, maybe from the atmosphere, maybe from other equipment, or you get a simple software bug, and suddenly the sensors are feeding the DP system a false position. The computer, trusting its eyes, will then try to correct its position by driving the ship to a place it isn't supposed to be.
You have to remember, the computer believes what it's told. One of the scariest scenarios is a frozen sensor. The data just stops updating, so the ship could be drifting off position, but the computer screen says it's perfectly still. Then, all of a sudden, a new, correct position comes in. The system sees this huge difference and thinks it needs to correct it fast. The result is a sudden, massive, and incredibly dangerous maneuver.
And that leads us straight to the center of the whole operation. Let's move on. Section 4, the computers. The brain problem. And a failure in the brain, while it can be really subtle,
Just look at what causes these computer-led drift-offs. We've got hidden software bugs and weird, unexplained system anomalies causing just as many problems as a bad software update. We're talking about gremlins in the machine that you just can't see coming.
This shows you how a ghost in the code can become a very real problem. A software failure can make the deep computer lose control of the thrusters, or maybe it starts rejecting all its sensor data. Now it's flying blind. All it can do is fall back on a mathematical model of where it was a moment ago, a model that becomes wrong the second the wind shifts. But the absolute worst-case scenario is when a software error does something truly terrifying. It commands uncontrolled full thrust. That's the brain telling the muscles to go completely haywire. There is no automated fix for this. Only one thing on the entire vessel can stop it.
And that brings us to the final and most critical part of this whole system. Section 5. Your watch begins. We're talking about the human in the loop.
This quote, it comes straight from an official incident analysis, and it's the most important thing you'll hear all day. The severity of the drive-off depends entirely on the data provided from failed position reference systems and the reaction times of the operator. The machine creates the problem, you have to provide the solution.
So here's the bottom line. After all the complex computers, all the alarms, all the backups, the last line of defense is a sharp, skilled operator, someone who can recognize the signs that something is wrong, trust their gut, and have the confidence to hit the big red button and take manual control before a small problem becomes a disaster.
Which leaves us with one last question to think about as you take the helm. In a world full of incredibly powerful, incredibly complex automations, when those systems fail, who is truly in control?